In this presentation on gradient control on submarine fan growth, I'm going to focus on the distributive part of modern deepwater fans and how depositional gradients influence their architectural styles and facies distribution. It's part of an integrated effort from a multidisciplinary team at ExxonMobil called process stratigraphy. It's made of geologists, engineers, and computational scientists. One of the motivations of this study is to provide adequate depositional models for deepwater fan and reservoirs, knowing a set of initial settings like initial topography and grain sizes available. I will provide examples from the field and compare them to numerical model results. We are going to review 3 case studies in this presentation. There are submarine fans on modern seafloors that represent the traditional end members of the steep sandy fan, that's for the Golo system, the large muddy fan from passive margin, the Zaire Example, and a mini-basin example, the Brazos-Trinity fan system. These examples could somehow fit in the categories of mud versus sand-rich fan models. But there are limitations to bring to this point, as we've discovered that large mud-rich fans are actually growing out of smaller sand-rich fans. It is important to understand that there is an evolutionary trend to these systems. As muddy as they are, the big fans are still sand-rich in their channel fields and distributive systems. On the other hand, sand-rich fans have distributive systems on relatively high gradients. The way sand and mud are partitioned in distributive systems from low or high gradient is very different. And this is what we are going to investigate through our 3 case studies. First, we are going to look at the Golo steep sandy fan example. The Golo submarine fan is located on the eastern margin of Corsica in the Mediterranean Sea, in a trough large of about 30 kilometers and dipping to the south. Depositional gradients at the edges of this fan are still around 1 degree angle. The shelf is narrow, 12 kilometers at most, and alpine reliefs stretch along the coast, feeding rivers and deltaic plain with coarse gravels and sands. It's interesting to note that the modern shelf is sandy, while mud is carried away by strong currents towards the north and deposited along the slope and in basins as blankets, mounds, and drifts. There is a direct pathway for fluvio-deltaic sand to short canyon heads and shelf edge gullies when the relative sea level is about 40 meters less than today. We are focusing on the most recent South Golo Lobe Complex because it's been cored entirely and imaged by a network of 2D high-resolution seismic lines every 500 to 800 meters, allowing a full characterization of its architecture. The resolution of this seismic allows us to depict beds that are 1 to 2 meters in thickness. The image on the left is a time thickness map of the Lobe complex. The core GDEX 6 penetrated 50 meters of deposits. The maximum thickness is around 55 meters. The cross line and deep line to the right show that the Lobe complex is made of 6 lobes deposited in compensation. Internal structures suggest succession of prograding, aggrading, and retrograding units, but also further details like channels, levee-like deposits that have not been described in lobe environment yet. The core shows a very sandy lobe complex, mostly made of sand at 85%, with grain size ranging from very fine to gravel, mostly medium. There are some plurimeter scale intraformational mud units separating the sand, described as homogeneous silty clay. When looking at the succession of lobes as mapped from Seismic and their relationship with the core, we can see that the lobes are entirely made of sand, even on their margins, while the 3 meters mud represents the fringe of a lobe that retreated 3.5 kilometers away. More actual penetrations of lobe shows the coarsest grains. The seismic data allows interpretation of the internal architecture of lobes at the lobe element scale. Here is the example of lobe 1. On the most proximal cross-section, in the upper right, we observe a stack of pretty incised feeder channels. Their thickness is about 15 meters. The expression of these channels somewhat disappear down dip, where reflections are mostly subparallel, with evidence of lateral shift in the main depocenter of the lobe elements. On the deep section, it's striking to observe the general aggradation and retrogradation of each and every reflector. The first lobe element is deposited the furthest downslope, and subsequent lobe element retreat behind it. The same observation can be made for each lobe. Each of them is made of truly unconfined mouth bars fed by aggrading feeder channels. Note that we still observe channelization 2/3 down the lobe. To sum up the Golo modern fan study, we differentiate lobe complexes at the end of channel-levee systems that are made of very sandy lobes deposited in compensation with a substantial muddy fringe to each of them. Lobes themselves are made of retreating lobe elements. Each lobe element is characterized by an incised feeder channel that becomes conformable as it transitions to a mounded mouthbar deposit. There is no distinction between the mouthbar fringe and the distal levee of the feeder channel. Additional information on the relationship between flow and deposit in these steep sandy fans can be obtained by tank and flume experiments as well as field observations. On the left, Hamilton reproduced retreating mouthbars in tank with a channelized turbulent flow. The flow, initially supercritical, undergoes a hydraulic jump, circled in red, when enough mouthbar relief imposes a change in flow regime to subcritical. Deposition occurs at and beyond the jump site, forcing the jump to occur further and further up dip until the flow is choked and moves to the site. On the right, in the Squamish Delta and fjord environment in British Columbia, this phenomenon was observed as it played out over the sequence of several days as seafloor imagery was acquired by the team of John Hughes Clarks. In addition to show net erosion in the channel colored in black on the map and net deposition at the channel lobe transition colored in white, we clearly see the expression of upstream migrating bed forms all over the channel and channel lobe transition zone. These bed forms have been reproduced in flumes and characterized as cyclic steps and long antidunes by Fedeli et al. They are all associated with supercritical flow regime. Post-mine collaborators described their 3D geometries, facies, and dimensions and found multiple expression in outcrops. The process stratigraphy team in ExxonMobil developed a depth average model for turbulent flow based on Parker's equations. The model run on the right shows the evolution of bed elevation and sediment load in a continuous flow on a 2-degree slope angle with grain sizes very fine to medium. A succession of lobes are being formed, with a central channel first prograding quickly, then retreating while depositing. Bed forms are formed all along the deposits. Interestingly, an erosional front propagating up channel towards the inlet is formed during phases of mouthbar retreats. With these observations, we can propose a more generalized depositional model for high gradient systems. They go well with a line source basin or input, because in such configuration, each entry point in the basin is short-lived, limiting the progression of each system to the basin floor. There is an idea that each fan starts depositing on high gradient on the slope at the early stage of its development and is then dominated by these sandy distributive systems fed by erosional feeder channels. Deposition would be triggered by the slightest change in gradient from a rugose substrate like previous deposits, top of an empty sea, or even inherited reliefs from deeper structures. Let's move on now to the vastly different case study representative of fans building on very low gradients. The Zaire modern fan develops on the basin floor of the West African passive margin, straight from the perennial inputs from the Congo River. On this bathymetric map, you can see the modern channel directly linked to the river upstream by a deeply incised canyon. The meandering channel stretches over hundreds of kilometers before reaching its terminal lobes by 5 kilometers of bathymetry and gradients around 0.2 degrees. Numerous abandoned channels are also visible, representing a long history of fan growth from the lower slope to the abyssal plain. The modern channel didn't build its long stretch all at once, but rather prograded by steps with abandonment and bypass of ancient terminal lobes. This was evidenced by the study of 2D high-resolution seismic acquired across the entire fan during the Ziongo surveys. The modern distal lobe complexes were sampled by Ifremer and studied in details. In his PhD, Bonnell shows the absolute age of individual lobes and lobe complexes, to the left, who appear to be mostly prograding. Note the dimension of the ensemble, 30 by 70 kilometers. Very big. Backscatter imagery revealed central portions dominated by distributary channels, contrasting with the more diffuse and feathery-looking bodies in their surroundings. Drop cores showed sand dominantly in the distributary channels, while muddy, silty turbidites, debris and slumps were described all around with a transition as sharp as the change in reflectivity colors. While it's expected to find thinly-bedded turbidites on the marginal portions of lobes, debris and slumps raise questions. The 2D high-resolution seismic lines acquired across the lobe complex also show a sharp contrast in seismic facies between what's interpreted as distributary channels stacked with high-res amplitudes and semi-continuous reflections, and the transparent, almost chaotic character of the rest of the body. The seismic gives us an estimation of the maximum thickness of the lobe complex, around 80 meters. Not too different from what we measured at the Golo complex, just much more widespread. To make sense of these contrasting facies, we've compared our observations with other systems. Here, for example, are backscatter images and cores recovered from the Mississipi Fan terminal lobes. Graded sand and empty dichaotic silts are also expressed in cores here, and the feathery-looking aspect of the deposit is striking. Perhaps the explanation is to be found in the growing number of literature referring to hybrid beds or debrides in the lobe fringes as a result of flow transformation from turbulent to laminar. This flow transformation seems to be occurring preferentially in unconfined settings and on very low gradients. For the Zaire lobe observations, it could represent a large portion of the deposit, maybe 50%. The EM strata depth average model hasn't been designed to handle flow transformation. This model run on very low slopes with very fine grains might just be representative of the channelized portion of low gradient distributive systems. Indeed, it shows many distributaries, some branches being active at the same time. There is no expression of large bed forms. The main flow is subcritical, which means the main channel could backfill long distances with sand before abandonment. The generalized depositional model for low-gradient fans attempts to capture all these learnings. It's represented with a well-established drainage system connected to the basin via a point source, which is a canyon incising the shelf. The fan is made of elongated meandering channel-levee systems, which can be filled with sand, ending and prograding over large distributive systems, where sand is only present in small distributary channels. The bulk of the deposit all around is thinly bedded sand and mud or slurries. Our last example has elements of both high and low gradient systems as it develops on rapidly changing slopes. It's the East Breaks mini-basin example from the Brazos-Trinity depositional system in the Gulf of Mexico. There, the perpetual movement of salt during and after deposition gives shape to interconnected mini-basin, steep on their side and very low gradient in the central portions or distal areas. We are focusing on Basin IV and its most recent upper fan deposits. The upper fan measures 16 kilometers in length by 8 kilometers in width and has a maximum thickness of 75 meters. Ultra-high resolution 3D seismic was collected over Basin IV, along with piston cores, allowing its dissection into key stratal elements. Note the transition from relative high gradients at the entrance of the basin to very low gradients in the distal portions, and even reverse gradients as the fan laps onto the opposite side of the basin. Spectral decomposition methods and horizon slicing through the upper fan shows an evolution in depositional styles from the early and late stage of the deposit. The lower complex is only deposited on the steeper proximal portion of the basin. It shows an array of bifurcating channels ending with paddle-shaped lobes. As we progress up section and on decreasing depositional gradients, we can see elongated channels ending with well-developed lobe bodies with multitudes of small distributary channels. These schematics are meant to show the progression of depositional style in the Basin IV of East Breaks, from the high gradient type to the low gradient type, as slopes decrease along the basin, but also through time as basin is filling. In the end, we end up with low gradient depositional style overlying the high gradient style. Something that we can probably generalize, as the tendency of any system will be to lower its depositional gradients through time. Systems with mixed gradients, like mini-basin, will evolve from short-lived bypass erosional channels feeding sandy, retreating mouse bars to longer-lived channel-levee systems feeding ever smaller distributary channels and their final transitional flow deposits. To wrap up this presentation, I'm proposing a set of 3D block diagrams for turbidite fans, which shows the evolutionary part of a large fan if given enough time to develop and spread on the abyssal plane. Initially, this large fan would start with small distributive systems perched on high gradient slopes, fed by short bypass erosive channels dominated by supercritical flow behaviors. This means retreating mouse bars, and this is also the time where supercritical bed forms would be preserved in the deposit. The mud is dissociated from the sandy mouse bar and deposited as fringes to the lobes, or carried downslope. With time, longer-lived sediment pathways establish at the shelf edge, allowing the generation of clusters of larger distributive systems on the slope, still dominated by supercritical behavior, but smoothing the depositional gradients enough for channel to prograde. With channel elongation goes levee growth and meander development, all contributing to progradation of the system to lower gradients. The distributive systems start to show the behavior of low-gradient systems with numerous distributary channels and incorporation of sandy and muddy slurries in the deposit. In the end, a mature canyon connects to a channel-levee system, feeding large distributive systems on the ocean floor. Sand accumulates in a grading channel locations and the proximal part of distributive systems. Big levees grow over previous terminal lobes, and occasionally an avulsion can create local increase in gradients capable of small or short-term reset of the system. All in all, submarine fans naturally evolve from high gradient to low gradient behavior as cumulative sedimentation reduces depositional gradients through time. Extra-basinal factors can decelerate or even reverse this evolution by keeping gradients high through tectonic uplifts or subsidence, or even if major collapses force a reset of the system. On the other hand, factors that enhance sediment supply, like climate or the development of a point source, can accelerate this evolution. I thank you for your attention. If you have questions about this work, I will gladly answer them now.
Thank you, Gwladys. You managed just and quite in time. It was a fabulous, beautiful overview of various fan models, and I'm particularly stunned by the datings of the Golo fan. That's really something. Can I ask you these precise datings? Can you correlate these with periods of wet climate in the Mediterranean? So relating the input to the fan lobe development?
Yes, I haven't done that work, but it has been published by Sohm et al. And other authors. I think there are some authors from the Netherlands as well. Joop did some source-to-sink analysis on the Golo system. And yes, you can relate the basinal inputs to change in climate in the continent. But what I see in Seismic is that the fan is active or actively depositing sand in the basin when sea level is relatively low, when you have that direct connection to land. But there is a climate part to this as well.
Okay, well, I think we have to leave it here. It's thank you very much, Gwladys, for this fantastic presentation.